we'll be looking at integration by parts. Right. So first of all, I'm going to define the formulas and where the formulas come from, and then I'm going to show you a method that will simplify applying these formulas. As we understood, we differentiated u and v with the product rule, and we came up with this expression. Okay, this line here is just the product rule as we learned it in chapter for differentiation. Now we're going to rearrange this equation and subtract v times du by dx from both sides. So we end up with this expression. Then we'll see that now we can put the integral sign in front of each and every term. We can do that as long as we put a dx at the end of each term. This dx will cancel away that dx, 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 and dx cancel away. So what are we left with? Is these cancelling away, because that means nothing, because that's just because of the dx in the denominator. So we get this expression here where we have u and v subtracting integral of v du by dx times in with respect to x and so on. So in fact we can leave these integrals cancellations alone and think of our integral to be this section here given on the right side of the equation. Okay, so we are going to, if we were given this two terms here, one term which is we're going to call dv by dx, another term u, and dx comes with the integral. We are going to go from right hand side to the left, but this at the minute looks rather scary and not so good looking. Alright, so no matter, we're gonna simplify it. So I'll show you, you'll find this formula given to you in your formula booklet. I'll show you how it can be simplified. Alright, so this is the formula. And if you think about this, actually, the second there we got another integral now. We turned one problem into another difficult problem. This du by dx. I know, I changed the terms. I just called it dv by dx, du by dx. Doesn't matter. Change of name, it's the same thing. It's the same formula. Okay, so I'm gonna show you that this integral here, where you have u dash times by v, is the second row on this table here. And this uv is multiplication of this u by this v here. Okay, notice I put a minus sign here because there's minus sign in the equation, in the formula. This second integral, purple, can be turned into yet another integral with the same rule. You have u dash multiplied by integral of v here, and you are going to, because of the negative sign multiplied by another negative sign, add this integral here, which I'm going to put in red there. Okay, so that red integral is the last row here, integrated. So there is only one integral sign here. Don't confuse that. Integral of u double dash with integral of v. Notice we started with dv dx, that's why this turned into original v, and now this is one step higher than the original v, that's why I put an I there. Then if we continue that, we'll get same thing happening again. You notice why I put this fractal picture here, because this is turning into a self-repeating function, and we've got to stop it somehow or another, because I know for a fact that this blue integral can yet be written with another integral and yet turned into yet more difficult problem. We've got to stop this recursive methodology here somehow or another. Notice we always have to integrate the last row of this table. Yes, this is the first product here. This is the second product here, which has a minus sign. Notice that this third product here has a plus sign. So notice that these signs uh, change, they alternate because of the negative signs multiplying with each other. Okay, so there are three ways that we can help stop this recursive function. Okay, so how are we going to do that? First method is when we get a zero in the differential function, this differentiation table here. If we have somehow differentiated a function such as, let's say this was u was x squared, we would have got 2x here, we would have got the 2 here, and the derivative of 2 would have been a 0. If we make sure that we differentiate one of those factors that differentiate to 0, our final integral will be multiplied for multiplication of 0, and that will simply stop that integration formula. So that's a good method. Maybe we can do that, maybe we can't. What if we can't? Alright, we can stop this integration another way. What if we have some powers of x that can be multiplied with each other? For example, maybe we get x squared multiplied by 1 over x. In this row here, this row can be integrated with respect to x, because if I have integral of that, that's simply integrating x power 1, and thankfully that can be done easily. All right. So that's the second way that we can stop it. We need only one of these methods, one of these options, either option one, either option two, or the worst case scenario, which rarely happens in A level, a row may repeat the original integral. I'll show you that with the last example. This third option is highly unlikely to come up with A level, but I will show you that in the last example. Let's start with a simpler example. X multiplied by cos x. Now, why would we integrate this integral in the parts rather than derivatives and antiderivatives and reverse chain rule or substitution? Because x is not a family of trigonometric functions, and x is a polynomial, and because a trigonometric function is not a family of x, there's no way one is not related with the derivative. They're not derivatives of each other. Therefore, we have to integrate this by parts. Therefore, we are going to put this x in the derivative or the differentiation column here on our in our table. Notice that I always put the differentiation on the left hand side and integration on the right hand side. This method is also called DI method because we usually put our derivatives on the left column on the left. So if we call our x the factor that will differentiate, it will differentiate to 1, and then 1 will differentiate to 0, like so. At the same time, we have to integrate cos and substitute that into the equation. So we said that we have x multiplied by sine, that will be our u and v multiplied with each other. Then we have to subtract this integral here, which will simplify to, we know what's the integral of minus sine is simply minus cos. Or if you like it, you could have put that into the table and just integrated sine there and multiply these two terms with each other. It would have given you the same answer. And finally, what we said needs to be done is that cosine as it doesn't need a negative sign because the negative sign is coming from here. And when we said we always integrate the last row here, integral of 0 times cos is simply 0, so we don't need to write it. Finally, this should be our final answer there. Integral of cos sine is minus cos. My bad. Alright, so we add a plus c because this is indefinite integral, an indefinite integral. Therefore, here we are looking at the second example. We've got x squared multiplied by logarithm of x. Now, if you try to differentiate log of x, you're going to get 1 over x. Then you're going to get negative x squared in the denominator, and the powers of x in the denominator will become more and more negative. So we're not going to differentiate log. We're going to put x squared in the differentiation column and log in the integration column. Okay? Subtract the value of uh, the integral of sine here. So if you remember what we discussed in differentiation chapter, the derivative of sine is cos, derivative of cos is minus sine, derivative of minus sine is minus cos, and all these have x's in front of them. So what we are doing, final step, will take us back to sine again. So derivative of minus cos would have been a sine. If we go back up a step, sine will have an integral of negative cos. Okay? And that means that there is negative in front of this integral and there is another there, and the sine itself has a minus cos as the answer. The integral of sine is minus cos. So we are going to get a plus cos because of the two negatives multiplied with each other. Okay? So as you see on the table, we could have simply read the answer from the table above. This negative sign times this negative sign would have given us a plus sign here. And integral of the last row, because of the 0, is 0. So we don't need to write the integral of 0 times cos x, or rather 0 times minus cos x. Okay? So we put a plus c in front of the final answer because this is an indefinite integral. Let's look at the example number 2. In this case, we've got x squared multiplied by log x. What do? We have options whether we can integrate x squared or we can integrate log x. Which one do we do? If I integrate x squared, I'm going to get higher powers. That's never going to end. But notice I told you that we also have option number 2 here, where we can integrate any row. If I integrate, well, I don't even know what's the integral of log x. So let's write log x under the differentiation column and differentiate log of x. We're going to get 1 over x. If I integrate x squared, I'm going to get x power 3 divided by 3. We said we need to have a plus minus here. Now, the first two product in our answer will be these two multiplied with each other, log x times a third of x cubed. Finally, we can we multiply these two terms with each other and integrate them? Yes, we can. Therefore, the answer is log of x multiplied by a third, or a third of x power 3, minus the integral of what is x cubed multiplied by 1 over x. I'm going to put the 1/3 at the front, in front of the integral, and write simply x squared because product of x cubed with 1 over x is x squared. And I'm going to put a dx here. I'm going to have to just carry these first few terms over again. I'm going to put the 1/3 in front of the log and write x cubed here. I'm going to put minus a third here. What's the integral of x squared? X to the power 3 divided by 3. So I need another third here. And that's it. This is our answer with a plus c. We can tidy things up and factorize common factors. We have common factor of a third x cubed that we can pull out of this expression. We'll have log of x. We're going to put absolute signs on the x because we cannot have negatives in the log function. And we'll have to subtract 1/3 here so that everything works out with a plus c here. Alright, so let's look at the next example. In this example, we are integrating x squared multiplied by e to the power of x. We have options here. We can differentiate x squared and integrate e to the power of x. Well, why do we not do it the other way around? Why not have e to the power of x differentiated? Because that would simply give us another e to the power of x, another e to the power of x. And if am being devil's advocate here, I know this is the wrong answer, but I'm showing you why we don't want these expressions going under the uh, integral. We don't want x squared here because the next term here would be 1 over 12 times x power 4, and the powers of x will go up and they will never disappear. Therefore, that's the wrong choice to make. We are going to put the x squared under the differentiation column and put e to the power x here. E to the power of x is going to integrate indefinitely as it is. Each step is a different integration. Here we're gonna have plus and minus signs here, and the next term would be 2x, next term would be a 2, the next term would be a 0. Therefore, this final row of integral is going to have no effect because we have a 0 there. We read our answer as these two terms multiplied with each other, these two terms multiplied with each other, and these two terms multiplied with each other. Obviously, every term has a factor of e to the power of x. So I'm going to factor that out and write e to the power of x multiplied by x squared, take away 2x plus 2. This is the simple form of writing the answer to the problem of x squared e to the power of x. Because this is an indefinite integral, we have to put a plus c at the end. Right, so let's look at the next example together. Right, in this example, we do have to integrate log of x, but we, we only know what's the derivative of log of x. We found that the derivative of log of x was 1 over x. So, why are we dealing with this in this particular situation when we've just learned integration by parts? Because that's the only way we can integrate log of x. We know its derivative is 1 over x, and we don't have any other factors multiplied by log of x. So we can pretend there is an invisible 1 there. That's not a bad choice. So we can differentiate log of x and we can integrate 1. Now, at the first instance, this may not look like a very sensible choice because the, the next integral is x, and this would continue if we couldn't integrate the row. But at this stage, we know that we can put an integral sign here, and x multiplied by 1 over x will simplify to 1, and that would be the last integral that we had to deal with. Therefore, The final answer is simply log of x times x, replacing those values from u and v with each other, and the integral of 1, which is with respect to x going to be an x. The minus sign is there because the formula tells us that we have to subtract it. Okay, so actually this is the indefinite integral, but we don't need a plus c because we have choices for our limits. We have 2 and 1 to substitute into that expression. So we are going to take that expression now and use the answer that we found in the last page. We're going to substitute 2 and 1 into those limits. We know log of 1 is 0. 0 minus 1 leaves a minus 1 here. Okay, and finally adding and subtracting and simplifying, we'll get the answer to be 2 log 2 minus 1. Of course, you could have written this as log of 2 to the power of 4, 2 to the power of 2, which is a 4, like so. That's also simplified answer. Now, I did promise you that I'll show you an example where we'll have a row repeated and an integral of a row repeats the original integral. So let's look at this example. These two functions e to the power x and sine x are in no way a family of each other. They're not the derivatives of each other and they're not the integrals of each other. That's why we have to throw them under the integration by parts. We'll differentiate e to the power x and we integrate sine. We do the same thing, the same step again, and we end up with, as the last row here, with e to the power x times sine of x. Now, luckily, there is a minus sign there. Therefore, if I pull out the answers for you, we have this product here, e to the power x times negative cos, which is there. Then we have a product of negative e times by negative sine. That's why there is a positive sign here. And finally, this integral. Notice this integral is exactly the same as that, the original question itself, because the sine of x does converge. Okay, and what do we do in this case? We can take this integral from the right side and add it to the left, because they are one and the same thing. We'll get 2 lots of the integral. The final answer is what we have on the right divided by 2, and we can put a plus c there. We can also factorize the power of x and rearrange sign and bring the cos next because that's got a negative sign. Alright, I hope you found this video helpful. I'll see you in the next section of the course.